Have you ever wondered why a tonal shift occurs when a car speeds by you on the street? Well, this is something called the Doppler Effect. But before we can fully understand this effect, we should take a look at waves. A wave is described as a disturbance that travels or oscillates through a given medium while transferring energy. Each wave has something called a wavelength, which quite literally is the length of a single wave. This is measured from trough to trough or crest to crest, or a single arbitrary point to an equal arbitrary point. Along with the wavelength, every wave has a frequency, which is the amount of single waves that oscillate in a set measure of time, let's say seconds. Therefore, a longer wavelength equals a lower frequency, and a shorter wavelength equals a higher frequency. If you multiply the wavelength by the frequency, you get the velocity of a wave. With this understanding, we can begin describing what the Doppler effect actually is. For this explanation, we will use sound waves. Let's take Shaw. He's in a stationary position, as are you, singing or screaming a single flat note. He is creating sound waves. They exit his mouth at a set frequency because the pitch of his voice stays the same. Once you start moving Shaw around, however, the frequency of his voice changes because the waves on one side of him are smushed together, creating a higher frequency while the waves are spread apart on the other side, creating a lower frequency. In Shaw's perspective, he is emitting a sound with an unchanging frequency and an unchanging wavelength, but because he is moving relative to you, the audience, you hear a changing frequency as he gets closer and eventually passes you. The same exact effect takes place if the sound source, Shaw, stays still while the perceiver, you, moves relative to him. The Doppler effect is quantitatively signified by a specific set of equations, where Vs is the velocity of the source, V0 is the velocity of the observer, V is the velocity of waves, F is the actual frequency of waves, F' is the perceived frequency. Although we focus specifically on sound waves to describe the Doppler effect, this effect is viable for every form of waves. For example, if you put a motorboat in perfectly still water while it stays in one position, the vibration of the motor will cause the pulsation of water waves in an outward circular motion from the boat. The frequency of these water waves will stay constant as long as the boat doesn't move. Once the boat starts moving forward, however, the waves in the front will be closer together while the waves behind the boat will be spread apart.
Science in action!
Did you know that because of the Doppler effect, astronomers were able to determine that the universe is expanding? They did so by studying the light that is emitted by stars and galaxies. Luckily for us, light is a wave. If this is true, that the universe is expanding, then everything should be moving away from a single point in space. Therefore, the frequency of light on one side of the star, as the star moves away from us, should be lower than that on the other side of the star. The electromagnetic spectrum shows that certain frequencies of light result in different visible colors. If a star is stationary, along with the Earth, that star will look yellowish. But as soon as it starts moving away from us, the frequency drops, making the star look a bit more red than usual. The color red has a lower frequency on the electromagnetic spectrum. If the star was moving towards us, the color would shift to blue. This is called a redshift-blue shift effect on stars. This is the exact reason how Edwin Hubble was able to quantitatively determine that the universe is expanding. Now you know the Doppler effect.